In competitive cycling, aerodynamics matter a lot. It can easily be the difference between winning and losing. And in recreational cycling, aerodynamics is also important because drag makes it harder to cycle, and who wants to use their legs? And from aerodynamics point of view, it is very complex because while you might want to draw parallels to something like a car, cycling has an additional element too, the leg position of the rider. So you get an even more complex aerodynamic response as you cycle along. But like cars, understanding what its aerodynamics are like from head-on wins most of the time, that's a bit different to reality because in reality there's a crosswind element too. That then means that the geometry the flow sees will be different to begin with. In this podcast, we'll look at how crosswinds and with varying leg positions affect a cyclist's aerodynamics, so the drag and all various quantities. And the data presented here is pretty thorough. We get a lot of different forces and wake surveying data so you can see the flow, how it evolves over time. And this paper we are using for this data is called The Influence of Crosswinds and Leg Positions on Cycling Aerodynamics. It is open access, so you can find the link below, and the DOI is at the top of the page here on the top left. So this work is experimental, which gives the authors one major advantage, and that is the material the clothing is made of. That's a good representation of what a cycling suit is. So they put lycra on a dummy, and we can see the microscopic view of the lycra stitching here in figure 2. And just as a side note, lycra is incredible to me. The amount it can stretch and still not let the wearer down is mind-boggling. Now, the dummy also has typical cycling helmets and shoes on. And taking into account this material and the shoes, etc., and hence the roughness, in CFD would be very difficult to do. Experiments take that difficulty out of the equation because it's already there inherently in the system. And then when you think about the shoes just from a meshing point of view, that takes a lot of cells as well. So experiments really give you quite a lot of advantages here. Now, for the way they tested it, the wind tunnel they used was pretty good. It was a closed return one, which means that it is in a loop, and the air can continually flow around. One of the major benefits of that is you don't need to use as much energy to get the flow to the speed you want because you don't have to accelerate the flow from rest to the speed you need. The flow hitting the fan is already moving around because it has been sent down the tunnel already and now it's returning back into the fan. So a closed loop wind tunnel is usually more efficient than an open loop, and pretty much always. So the tunnel itself was 2.5 meters by 2 meters in cross section, which is a very good sized one. And the flow speed could go up to 40 meters per second, which is pretty good for a tunnel that size. But the tests were only conducted at about 50 meters per second, which is more representative of almost sprinting cycling. So that's about 55 kilometers per hour, and that's pretty fast for like a long distance sprint almost. Now, one thing that is impressive about this wind tunnel, but actually bad for this experiment, is that the turbulence intensity is only about 0.12%. That's very low and good for a nautical wind tunnel. However, when you think about the conditions that cycling takes place in, unless it's indoors, the wind will have some turbulence to it. And because this research is about crosswinds, that means then that, yeah, there will be outdoor situations, that's what it's for, and inherently some turbulence is associated with that. As a general rule of thumb, when you consider an object in a flow outside, around ground level, a turbulence density of around 5 to 10% is good. However, it could be way more than that. For example, literally today, while I'm recording this podcast, the wind is about 40 km per hour, and the gusts are about double that. So the turbulence density level is quite high. That means that conditions tested in the wind tunnel aren't quite representative of the real world application when you have a turbulence density this low. Now, is that bad? Well, it can be seen as that, but we also have to consider what kind of differences a different turbulence density will give here. So we're talking about cycling. Now in figure 1, where is figure 1 here? Here, figure 1 is after figure 2. So we see a cyclist. And in effect, a cyclist can pretty much be thought of as a bunch of cylinders stuck together. For example, the forearms or the upper arm is each a cylinder, and the head is kind of like a cylinder too, and so on with the rest of the body and the bike itself as well. There are a bunch of cylinders all around, and some are big and some are small. What that means is that once this flow passes really the front of the cyclist, the flow will probably be turbulent already. That's because these cylinders will produce large wakes. For For example, the front wheel is churning up the flow, and that flow is now going to be turbulent. That then flows downstream and hits whatever else is down there too. So here, while the oncoming flow conditions might be different, and in that the tempest density is much less than it would be in real life, it shouldn't have that much of an effect on the cyclist, because once you hit the first part of the cyclist, that the bike and maybe the head and their forearms, the flow after that will be turbulent anyway, and the differences will be faded away. So because this geometry is so variable and bluff everywhere, the major difference in turbulence intensity will maybe cause a 1 or 2% change in the results, if that. So I think this difference is okay here. And just for general interest, a time when this difference in turbulence intensity would be important would be when you have something streamlined like a wing or a plane. And just as a side note, if you'd like to learn OpenFOAM, which is a very powerful and completely free CFD software, then check out our courses here. But let's move on now. So one thing to note is that the authors did move the cyclist's legs in different positions as they tested, but the legs weren't rotating around with time. Instead, what they did was they set the legs to just a particular position, like for example here in this figure, and then tested this position with the wind, then they changed it to the next position, and so on and so forth. That will make a difference to the results because moving legs will create a transient effect that won't be captured here with these pseudo moving legs. What that means is that for these results, they're more applicable to when the cyclist isn't pedaling and they're just having their feet in certain positions. And that does occur, for example, going around corners or even downhill sometimes and so on. So these results are still valid, but for particular parts of the ride. And just like that as well, if you had to cycle, if you had a transient effect, those aerodynamic properties, those results, wouldn't be as applicable to cornering, for example, when the cyclist isn't rotating the pedals around. Now, the leg positions tested here were done in increments of 15 degrees and in a 360 degree revolution. So that's 24 different positions. And in figure 3, we see the wind tunnel setup and we see how the bike was mounted in the wind tunnel. So if you look at these little red things at the bottom, they are 4 very streamlined objects that pop up out of the ground and connect to the wheels. Now, this is one thing that is always tricky to do. So the designers of this system did a really good job here actually. They said to themselves, well, we want these supports to interfere with the flow as little as possible. How do we do that? Well, we need to make them streamlined then. And that is a very good thought process. If the supports are streamlined, then the flow will go around them as unhindered as possible. And that design is good, except it doesn't take into account the flow from the bike. So if you were to mount these supports in the wind tunnel and without a bike attached to them, that would be excellent. They're aligned with the flow's direction and so their wakes will be minimal. But when you add a bike and the dummy and the flow going over the legs, that will be then blowing out and plus being churned up. So if you look at the angle the flow will be hitting each support, it won't be exactly the same direction as the friction flow anymore. That's just part of the game. So if these supports are now seeing flow at that angle that is now created, that will then create a larger wake too. That will then affect the cyclist and general flow a little bit more. Unfortunately, there's no real way around this problem, and in figure 15, as we'll see later, we'll see how much the supports affected the flow. Also, the authors say that these struts were yawed with the rider too, so they're on this entire turntable. You can kind of see the outline of the turntable in the right figure here. There's very faint white circular line going around. So at non-zero angles of attack, the yaw angles, the struts will be at an angle to the flow too and will have more of a wake as well. I just wanted to point out this problem because sometimes it can actually cause severe problems. Anyway, in these pictures at the rear of the cyclist, we can see in the left figure, there's something called a rake of keel probes. And then in the right figure, something called 7-hole probes. What are these things? Well, they're instruments to measure the flow. First of all, the keel probe. So a keel probe is an awesome little device that you don't see too often, and you don't hear it talked about too much either. They measure the total pressure at a point in the flow. If you don't know what the total pressure is, then check out a video on our YouTube channel called Static Pressure, Dynamic Pressure, and Total Pressure Explained, Aero Fundamentals number 6. In that, we go through what the total pressure is, as well as how it's different to the static pressure and the dynamic pressure, and then how they all work together too. Anyway, The reason why the kill probe is so good is that it doesn't have to be aligned with the flow to get accurate readings still. So for example, something like a pitot tube also measures the total pressure, but it's very sensitive to the alignment angle to the flow. So the best pitot tube usually gives accurate results to within about 1% if you're within about a 30-degree cone angle to the free stream flow angle. And that's really the best angle that I've seen, like up to 30 degrees. I can't recall seeing anything better than that for a pitot-static tube. But for kill probes, some can give you total pressures accurately, even to like 100 degrees out of alignment or more to the free stream flow, or the flow direction anywhere. That's pretty amazing, and that fact is very important here because they have this rake of probes here, a bunch of probes in formation behind the cyclist, and here the flow will be awake. It will be churned up and at different angles all along the cyclist and with time as well, because the flow over the cyclist will be transient too. So if you were to have regular pitot-static tubes, that wouldn't measure the total pressure very accurately. The results would be very wrong actually. And you could go further downstream to make the flow straighter and make the pitot-static tubes more accurate. But also the further downstream you go, the more the wake has died out now, and you lose the finer details that have come out of the wake to begin with. So if you want details, you have to be closer to the rider, and if you're closer, you need kill probes then. And that is what the authors did smartly here. They figured that out, so that's very good. Now in the right figure, with the 7-hole probes, these are a different kind of probe. They have 7 holes, as the name suggests, and what these probes are used for is to calculate the 3 orthogonal velocities in the flow. So you can measure also the total pressures as well from there. You measure the total pressure and then you calculate the velocities from there. And in figure 6, we see the location of the kill probes and the 7-hole probes surveyed, so this grid here. And the red area is the kill probe, the area surveyed by these rakes of kill probes. And this area is much larger than the 7-hole probe area. And that tells us why they could have used just the 7-hole probes, but they didn't. And the reason is because they had fewer of them. And the surveying area has to be smaller then because it takes a lot of time. So the rake of kill probes could do a larger region because they're quicker. And that is one of the things that should never be underestimated when you're doing wake surveying. It takes so much time to do. Like, I've done some that have taken 10 hours, 14 hours per plane, and it can be very time consuming. And when you do ones that long, you have to make sure that everything works, because if you get to some point and then something fails, you often have to just throw away the results and start again. You shouldn't throw away the results, I should mention. You just don't look at them, but you should always keep results if you can, just as a reference. You never know if they come in handy. But anyway, you want things to work because you don't want things to fail at like the 13th hour. That's just a massive waste and pretty frustrating. Anyway, in figure 4, we see how the yaw angle of the flow is measured relative to the rider, this beta angle. Another thing to note is that there are the drag and side forces, but they are not aligned with the rider because they have been aligned with the wind's angle instead. So FA here is actually the drag like the rider will feel, and FN is the normal force, or the side force the rider will feel as well. And FA stands for axial force. Let's now jump to the results to see how the yaw angle and different leg positions affected the forces on the rider. So in figure 7, we see the axial force area, which is effectively the drag area the rider is seeing. Now, the top left plot is for yaw angle of 0 degrees, the top right is for 10 degrees, the bottom left is 16 degrees, and the bottom right is 20 degrees. There are 2 colored lines here too, a blue one and a black one. The blue one is for crank angles, so the pedal is moving from 180 degrees to 360 degrees, and those values are on the top x-axis here. The black line is for the crank angles between 0 degrees and 180 degrees, so the first half of the cycle instead, and those are given on the bottom axis here. Now looking at these plots, you might notice that there is sometimes a mismatch between the blue and black lines. For example, in the bottom right plot, even when you take into account the uncertainty bars for the data, which it's great that the authors did that, by the way, well done to them, you can see that past about 90 degrees or 270 degrees, the 2 lines no longer match. There's a decent discrepancy there. The authors say that this was due to an asymmetry in the geometry. Now, I'm pretty sure this is referring to the leg position. So as you look at the plots, As the yaw angle increases, so going from left to right, top to bottom, this discrepancy between the black and blue lines increases. That's because one leg will be in front and hitting the flow before the bike, and the other leg will be behind the bike and being hit later, so it's in a wake effectively. So depending on the position of the legs, the geometry will not be the same if the left leg is cranked to an angle or if the right leg is cranked to that exact same angle. Anyway, let's look at the top left plot because this is at a 0-degree yaw angle. The rider is straight on to the flow. This shows that the worst leg position is at 90 degrees and 270 degrees. That means that when one knee is up and the other leg is completely extended downwards, then either side of that, the axial area drops off. So if both legs are partly bent but not fully, that is the lowest drag position. So that's at about 15 degrees or 180 degrees. And that alone is very interesting for going around corners. For example, if you want to brake later, you could take advantage of this graph with this higher drag and put your legs in the worst position so you can create more drag. That will then slow you faster, so you can carry more speed into a corner like you do with racing a car. You can slow faster and you can get through the corner quicker. So the takeaway message from this top left plot is that the lowest drag area is when both legs are partly bent, and the highest drag area is when one leg is completely bent and the other leg is completely extended. Let's now move to the top right plot, which shows the rider at a yaw angle of 10 degrees. Now the black line corresponds to the left leg being bent up and the right leg being extended. The blue line corresponds to the right leg being bent up and the left leg being extended. That's important because the left leg is exposed to the yawed flow, while the right leg is kind of shielded by the bike a little, and the left leg is too. I mean, the left leg is getting hit by the flow first, then the flow goes over it, hits the bike, more wake there too, and then it hits the right leg finally. So the right leg is not seeing clean flow. So here, the maximum drag area still occurs around 90 degrees and 270 degrees, but depending on which leg is being bent at lower angles, the drag area now changes. You can see a discrepancy between the black and blue lines. So let's say that the left leg, the leg that is completely exposed to the flow, is being bent up. So that is the black line from 0 degrees to 90 degrees. That produces a greater drag area than if the right leg were bent up, so the blue line from 0 degrees to 90 degrees too. That tells us that the left leg is producing more drag area along the entire cycle compared to the right leg, because past about 90 degrees, both legs produce about the same amount of drag area. So if you were to average this, the black line is worse, so the left leg is worse in terms of drag production. And that kind of makes sense because it's getting hit by the flow first, and that's going to create a larger wake as opposed to having a little bit more shielding as you go along. Anyway, that was at a yaw angle of 10 degrees. Going down to the bottom left plot, which is now for a yaw angle of 16 degrees, we now see a very different relationship. So at this yaw angle, there isn't really a very clear maximum or minimum. For the black line, you could say that maybe the left leg is rising up, so it's bending. That's creating a larger drag area. But interestingly, the blue line shows that as the right leg goes from completely bent to unbending, that is when you get the highest drag area. So this 270 to maybe 330 degree angles. So yawing the bike completely changes the trends that we saw in the top two plots here. But while this seems bad, if we look at the actual numbers on the y-axis, at this yaw angle of 16 degrees, the values are generally lower than the top two plots, which would then for the bike more into the head-on wind kind of situation. That tells us that the bike in a crosswind actually produces less drag area, generally speaking. And I'm not sure if that agrees with my experience in riding. I mean, I don't have too much riding experience. I find it really uncomfortable. But I guess from a physics point of view, if you're looking at an angle to the wind, the flow's force isn't pushing you directly backwards. So I guess that makes sense here, this lower drag area value. Anyway, in the bottom right plot, this trend continues and overall the drag area numbers are lower again. So I think we can really conclude that from these plots, there's a crosswind, that's actually good for drag reduction for the rider, what the rider is feeling, pushing backwards. And from this last plot, which is at a yaw angle of 20 degrees, when the left leg is going from half bent to fully bent to being unbent to unbending halfway, so this black line from about 70 degrees to 180 degrees, that's producing a little less drag area overall. Now we haven't seen any floaters yet, but I think that makes sense because in that situation, the leg will be covering most of the bike behind it anyway, so you're really just shooting it. Whereas for the blue line, which corresponds to the left leg, the leg is getting hit directly by the wind and it's extending down, so then it's just increasing how much stuff gets put directly into the wind. You have a much greater area and it's just like getting in the way more, I think. And it's not shooting the rest of the floor, rest of the bike and other leg as much, I think. Anyway, so these 4 graphs give us a lot of information. The first key takeaway is that it really seems like riding in crosswinds reduces the drag area. The second is that having the leg that is being hit directly by the wind bent up is generally better for the drag area. Now in figure 13, we see some FlowViz data and some wake surveying data. The top 2 figures are for the streamwise vorticity, which now it's important to note that these colored regions don't necessarily correspond to vortices. You can have vorticity without vortices, but it's most likely that they do correspond to vortices. And there's also, this is for no crosswind. The left plot is for when the cyclist has both feet about the same height off the ground. We can see here it's for 195 degrees. There seems to be larger vortices just behind that and one for each side of the rider, and each one is opposite sign as well. There seem to be, I think overall in effect, some kind of horseshoe vortex system is forming around the rider, and that's a macroscopic vortex system that really dominates most of the flow. In addition to that, there are minor ones forming here and there, little vortices. For example, if we look at the foot on the lower left, there's a fairly strong blue region. And if we look at the right figure, that blue region is growing in size and intensity. So this foot, as it pushes down, produces more into the wake and creates a larger vortex and a stronger vortex, it seems. And I think that's a pretty good takeaway message. Anytime you stick something bluff into the flow, you're going to get at least one vortex and probably 2 as the flow rolls up around it. So while there are a bunch of vortices around here, I think that the general idea of just having bluff bodies in the flow can explain most of them. Now in the right figure, the macroscopic vortices behind the rider become more intense. They're bluer and redder. So what I think is happening is that as the legs are pumping away, they funnel the air around the hips more, and that feeds these vortices with more energy. So the vortices get stronger. And again, we don't have the exact quantities to definitively tell that, but it's likely from these plots. And if you're wondering what the aerodynamic quantities we need to say for sure that these vortices are getting stronger, it would need to be circulation. That's the values we need. And if you don't know what the circulation is, then check out a video on our YouTube channel called What is Circulation in Aerodynamics? Aero is number 11. We go through what it is and how to calculate it. Now in the middle row, we see these B plots, which are the turbulence intensity, which is awesome. So what this tells us is that how much the flow speed is varying compared to the average flow speed. The right plot is definitely higher in terms of the turbulence intensity levels, and I think that's what that's telling us is that effectively the wake is just larger and possibly even stronger here. And if we look back to figure 7a, that really agrees with the plot of the axial force area. The 270-degree angle gave us the highest values. Now the reason why I concluded that the wake must be stronger here and worse in figure 13b on the right is because the flow speeds will only generally fluctuate dramatically in aeronautical wind tunnel when we have something messing the flow up. That doesn't necessarily mean a wake. It could be the flow is being messed up but somehow speeding up too, but that's highly unlikely. And given the location of these fluctuations right behind the rider, it's pretty much because of the wake. It's pretty likely. And because these regions were redder, so the turbulence density was higher, that suggests a stronger wake too. There's a lot more flapping going around, a lot more transients to the flow. So what I think we conclude from these plots is that having one leg up and the other one down channels the flow to worse places and creates a larger wake, particularly around the hips, and hence higher drag. Cycling, it's all in the hips. Now in the bottom row, the C plots show the normalized lateral velocity to the free stream flow. In other words, it shows how fast the flow is moving sideways compared to the free stream velocity speed. A value of 0.1 means it's moving at 10% of the free stream flow speed to the right, I guess. It means the right here, and that would make sense given the plots. Anyway, as we might expect, given that at 270 degrees, the wake is stronger. The lateral velocity here is also stronger. So the flow is shooting sideways more to take up that void created by the rider. So that makes sense, and really, I don't think too much of interest can really be gleaned here, but it's just generally interesting. Now in figure 15, we see, where's figure 15? That's 14, this is childproof. 15 is down here. Okay, let's zoom out a little bit because there are a lot of figures here. This is 15. In figure 15, we see some comprehensive wake plots of the total pressure coefficient at different crank angles and yaw angles. So here, the total pressure coefficient is highly indicative of how much energy is in the flow. A value of 1 means that at that point in the flow, it has as much total energy as it had upstream before hitting the object. So there hasn't been anything really sapping its energy away, or if it has sapped away, somehow other flows come in and given it its energy as well to boost it back up to 1. Now a value of 0 means that all the energy has been sapped away, and that's really bad for drag. Now something that might seem odd is that for every crank angle given, so down the y-axis here, on the left, as the yaw angle increases, so going from left to right, the total pressure coefficient obviously drops. And the reason why I say that is odd is because, as we saw earlier, how increasing the yaw angle dropped the resistive force on the rider, so the drag the rider felt dropped with increasing yaw angle. However here, this total pressure coefficient is not referring to the resistive force the rider feels, but also, in effect, the side force as well coupled with that. And now it makes much more sense why, as you increase the yaw angle, we seem to be getting more energy being sapped away. That's because it's not just the resistive force that's increasing, it's a side force as well that's increasing, as you expect. And the side force is not useful here, so it's really like wasted energy too. Now, going down the plots, so at different crank angles, at no and small yaw angles, so the first two columns, when one leg is bent, that increases the total pressure coefficient deficit in the wake. You can see that there is more blue here. But as your angle increases, the trend becomes less and less obvious. So we don't know from these plots and data, but maybe yawing the rider more and more reduces the variation in the flow's effects on changing leg positions. And I would certainly agree with what we saw in figure 7, where the more the rider was yawed, the flatter these force lines became. So just here you can see it was like bumpy, but then it went pretty flat as we yawed it from 0 to 20 degrees. So that trend might be true. And with that, we come to the end of this podcast. I think a few key messages here are that first, yawing reduces the drag felt by the rider. The second is that it also reduces the variability in the drag felt by the rider because that line gets flattened. And finally, third, cycling is all in the hips. Finally, did you know that we offer a service to simulate your very own car? If you'd like to do that, then check it out below. And if you're staying on YouTube, YouTube thinks you like this video, so check it out. Peace out, amigos.